All right, please take it away.
Thanks. Yeah, thanks a lot for the invitation. I think this is the closest I've been to giving an actual in-person talk in the last year. Just seeing people together in a room is kind of nice and refreshing. So yeah, thanks a lot for the invitation. I'll tell you about some work sort of making a connection between fundamental questions in deep learning and some tools we're borrowing from physics to try and answer them. So let me start by giving a lightning fast review of deep learning and supervised learning. I know Ethan covered some of this on Monday, so I'm going to go through this quickly, but if there are any questions, feel free to stop me now or at any point in the talk. So I'm going to be focusing on supervised learning, which is currently the main sort of paradigm for doing machine learning. And the idea of supervised learning is, let's take vision or image classification as an example. We are given an image. The image contains an object, which could be, let's say in this example, one of 10 possible objects. So it could be an airplane or a car or a bird or one of these options. And the task is to build a model or a function that, given the image, tells us what's in that image, what's the object in that image in a sort of multiple choice way in this case. So here, the images here are taken from CFAR 10, which is a standard image classification benchmark that people test their models against. And so it contains a set of like 50,000 images and their labels. More generally in supervised learning, we're given what we call labeled data. So these are pairs X, Y of inputs and labels or outputs. So in this case, X, the input are all the pixel values in the image, and Y, the output is the correct label or the correct type of object in the image. And the goal is to come up with a function F that given an input X predicts the correct label. And so here we're doing image classification. We can apply this to text. We can apply this to many different domains. And the way we do this in deep learning is really about how we structure this function to make these predictions. And we do that by creating what we call a deep network. So a deep network is essentially a function that's made up by composing several functions, some linear and some nonlinear, in what we call layers. So this is the simplest example of a deep network. We call this a fully connected network or a dense network. It accepts the input as a vector of real numbers. So again, think of each one of these as like the one color value of one pixel in an image. So the number of inputs here could be 3 times the number of pixels in the image because we have red, green, and blue. So that would be the input, and then it goes through a series of fairly simple functions. So each one of these connections, like the black connections, correspond to multiplying by a certain matrix. And then at the next level, we apply some nonlinearity, which could be sigmoid function or ReLU function. The details don't really matter. And we make a series of these until we have our output. It could be one output or multiple outputs where we try to predict the label. So here it is in functional form. We take our input X, we multiply by some matrix W1, and then we apply nonlinearity, call it sigma, and we do that multiple times with different matrices W until we get the output. So a neural network represents a large class of functions which are parameterized by these weights W, and we sort of need to learn these weights based on the data that we are given to match the ground truth or the underlying function that we're trying to mimic. And the way we do that is we turn it into an optimization problem. We write down a loss function L. So L is a function of theta. Theta here will be the collection of all the weights, all the weight matrices in the network. And we write down a loss function. There are different choices. And in this talk, we're going to stick to the mean squared error function, which says for sum over all the data points we have, for each one compute the function prediction on this input, on the image, and then compute the square distance to the ground truth, to the correct label. So this is a function that we're going to try to minimize. And the way we minimize this function is by doing gradient descent, typically in deep learning, which means initialize all the weights randomly, and then take successive steps. At each step, we're going to calculate the gradient of this function with respect to all the weights. We're going to multiply it by some parameter called the learning rate, which is up to us to choose. It needs to be not too big so that we're making small adjustments to the weights and we're staying close to this linear approximation that's happening here. And then we're just going to keep updating the weights until we get some function which will hopefully perform well. So this is the whole setup of deep learning in a nutshell. And the reason we're talking about this is that it works really well on many tasks. So this is an example of a similar task called Imagenet. So this is, again, an image classification task. It's just harder than the one we've seen before. So now we have a data set of about 1 million high-resolution images. And the task is to predict what's in an image, but not out of 10 classes, but out of 1,000 classes. So it's a much more difficult task. And here you can see how the error, so this is like top 5 classification error. That means take your favorite model, compute its top 5 predictions for the class, and just check if the correct one is in the top 5, rather than if it actually nailed it. So you can see how the best models, how the error evolved through the years since 2010. And you can see that around 2015, it beat human performance, and it just kept improving since then. The networks that are used, the best networks today, are not as simple as the simple dense fully connected network that we just saw. They're convolutional networks, but the basic ideas around loss function, optimization, and the fact that we're composing some simple functions to make a complicated function, these things are all the same. So the details of the architecture will actually not be important for this talk.
Question?
Yeah.
So how important is the choice of the loss function? Does that really matter? Can you just sort of pick it? Is it up to you? Should I think of it as some like Lagrangian that you're?
So as with all the choices, as you can see, as I present this, you can see there are lots of choices to be made in all of this. So loss function is one. How exactly we do gradient descent is another, like learning rate, and what's the architecture. There are lots of choices. They all matter. The currently sort of the best choice today seems to be not to use the mean squared error. For this task we're talking about now, is actually not to use mean squared error, but rather to use cross entropy, because I didn't present it this way, but you can think of these predictions as, you can think of these functions as predicting probabilities on the labels rather than predicting the labels directly. So that's just kind of a different way to phrase the problem. And then when you do that, you can calculate cross entropy and try to optimize that. And that tends to work better. It might be because the mean squared error function is kind of pretty sensitive to small changes in the weights. So for example, we know that mean squared error, you need to tune your learning rate more to get good performance. Cross entropy loss is like more permissive. So in practice, people tend to use cross entropy for this, but if you work a bit harder, you can use mean squared error as well. So that is all to say, yeah, this is one choice you can make. There are other losses you can use as well. You can stick terms to this loss, and they like regularization terms, and they improve things further. There are a lot of choices to be made, and there's not much understanding in the effect of performance, but not in ways that we really understand. It's more like kind of practical considerations. So yeah, so these results were definitely the latest ones were actually not using the mean squared error loss. They used the cross entropy loss. And the main thing, yeah.
A question about the human performance score, because wasn't the data set originally labeled by humans? I'm just curious about what that error is.
Yeah, that's a great question. So yeah, so I think so if you can take, so human performance is not a fixed number, because like one thing that's pretty clear, for example, is how motivated are the humans? For example, among these 1,000 classes, just to give a sense of what's going on here, these 1,000 classes are not all at the level of like car or truck or things like that. There are, for example, a lot of classes in there that are like different dog breeds. Okay, so then if you're looking, if you are tasked with labeling this data set, you have to know your dog breeds to get a good answer, right? And then the question is, how motivated are you? Like, are you going to sit and do a Google search on these images to try and label them correctly, or are you just going to guess, right? And so one way that people label these data sets is by using Mechanical Turk. So they do crowdsourcing, they pay people like a small amount of money to go and label, and then they do kind of an okay job, maybe a bad job, right? But then you can go and have people who are maybe more motivated to do this labeling work, and then they will maybe do better. But if your baseline is the mechanical work folks, then you will get a discrepancy between these two groups. Right, so this is where this comes from. This is like one group was Mechanical Turk workers, the other group was, I forget if it was like grad students or like an academic group that went through this, I believe. And so you get a discrepancy in the predictions because it's really a hard task. It's not like a task that every human will do at 100% level. So that's where this discrepancy comes from.
Okay,
it's like,
yeah, that's what I was wondering is, I guess it's a harder task than the labels you showed previously. And
yes, yes. Even with the ones you showed previously, if you look at it, there are definitely images there which are, I mean, there are just some that are just mistakes, which just the people who originally labeled them were just wrong. There are also some which are kind of hard to actually understand what's going on in the image. And so this is where these things creep in. Right. The thing I want to emphasize here is that we're training on some amount of data, and we're always testing on unseen data. So there's always a holdout set that we're keeping apart, and we're testing on that. And that makes the whole thing kind of, I mean, that introduces a kind of uncertainty into this whole thing that I'm presenting. I mean, there is a way to formalize it, but in the end, we're going to be testing our model on data that it's never seen before. And so that kind of introduces the main challenge of trying to understand how these things actually work and operate and how well they perform, because we're always testing it on unseen data. These are some examples of images from Imagenet. So you can see these are like high resolution images. In these cases, the objects are like pretty simple to figure out. But this is what they kind of look like. Okay. So what I'll talk about today. So what I'll talk about today is kind of how can we understand what's going on, and how can we understand theoretically the good performance of these models, because they perform very well. And kind of at a high level, the question is, how does that happen theoretically? More specifically, there is a sort of paradox here, which is called the generalization paradox, which is the following. So if you open a textbook on statistical learning, you'll see that there's what's called a bias variance trade-off, which roughly means if you take your model and give it more and more capacity, it's going to at some point be able to memorize all the training data you show it. And then when that happens, when the model is big enough, it's probably just going to memorize the training data. It's going to do really well on the training data. But once you show it some unseen data, it's not going to do well at all, because all it did is just memorize the specific examples that it saw. So you don't, the common law used to be you don't want to make your model too big, because then all it will do is memorize and not like learn anything, whatever that means. With deep learning, we found empirically that that's just not the case. You can take these models, you can make them as big as you want, really as big as you can fit in the computer, and the performance on unseen data is just going to improve. And it keeps improving even beyond the point where they actually really memorize all the training data. So the models are big enough to memorize the training data, at least for the smaller data sets. And yet, when you test them on unseen data, they work really well. And the bigger you make them, the better they do. So that's kind of a fundamental question that has been driving a lot of the theory in this field. Notice that it's not like a completely well-defined question, because you need to know something about this unseen data to understand even kind of phrase this question. It doesn't happen on any data that we have, but it does happen on natural data like images. So this is kind of a motivating question for a lot of these theoretical studies of what's going on. So there's a question to be answered. Then there are more specific questions that we'd like to answer. One is what ends up happening in practice is that remember that we have this learning rate here that we put in. And we'd like to find out how to set it, right? What number should we put in to get good performance? And it turns out that the answer in most cases is don't keep it fixed, but rather start with a fairly large value, train for some number of steps, and then after a while, change the value. While you're training, make it lower, decay the learning rate, and keep decaying it until you're done training. This sort of schedule for the learning rate ends up giving us the best performance in many cases. This is like the most common way to treat this. And so the question we can ask is why? Why does that lead to better performance? And then another question is, again, empirical observations show that there is a correlation between the performance of the final network and the local curvature of the loss function. So to be clear what I mean by that, we take our loss function L. This is a function on the space of parameters. We train the model, we go to the end, and then we compute the local curvature in this. This can be a very high dimensional space, so you can think millions, tens of millions, or more parameters, but we can still measure the local curvature. For example, we can calculate the Hessian of this loss function, and we can compute its maximal eigenvalue. This is something we can actually do very easily empirically, and that's one measure of the local curvature. And there are other measures which are actually better than that, or more correlated with performance. And so it has been observed that there is actually a correlation or a negative correlation between the curvature and how well the model performs. And that means that the flatter you are, the flatter the landscape is in the point you got to after training, the performance tends to be better. And that's another thing that's not completely clear, but it seems like a good thing to look at if we're trying to answer things like why does the network perform well. So a good theory would sort of explain these things, but it would also go beyond being descriptive. It would actually be predictive. For it to be useful, it would tell us, well, what is the best way to set the learning rate without actually running lots of experiments and just trying things randomly. So these are the kinds of things that a useful theory would tell us, and that's kind of we're trying to take a step in that direction. All right, so in this talk, I'm going to focus on this first paper, and I'm going to mention a couple of other papers which are related. Well, we'll see as we go on, but these are the main papers we'll talk about. Okay, so now let me give a bit more theoretical background that we'll build on in this talk. So one fairly active area of research in deep learning theory has been wide neural networks. So we talked about the basic neural network structure, which is that we have these layers of neurons starting with the input layer, and then we have these things that these are called hidden layers. These are like the intermediate calculations as we're composing our function. And then finally, we have the output layer. And there's the number of layers in the network is called the depth of the network. And depending on the network, the depth can grow fairly large. We have networks with hundreds of layers. With some tricks, you can even train networks with tens of thousands of layers. And so they can go fairly deep. But it turns out that there's a limit, which is more interesting, I would say, to study theoretically, and that is the wide limit. That is where we keep the number of layers fixed. We keep the architecture fixed, and we take these numbers of neurons in the intermediate layers to be very large. In the limit, we take them to infinity. And it turns out that's an interesting thing to do for a few reasons, or for two main reasons. One is that adding more and more neurons gives us empirical benefits. It typically makes the network perform better. So one good thing to do is just if you have a network that with certain performance and you want to make it better, one good thing to try is just increase the number of neurons. And just to be clear, increasing the number of neurons here really means taking these matrices, the weight matrices that we're multiplying by before and after, and just making one of their dimensions bigger. That's all it means to introduce more neurons. So at the functional level, it means make our weight matrices bigger. Okay, so we get empirical benefits. We also gain theoretical understanding over what's going on, and there have been a lot of works on this. So at a very basic level, the reason we get theoretical understanding has to do with the central limit theorem. So imagine we have a neuron here, and we're making this intermediate layer very wide. Well, that means that a neuron here is now calculating a weighted average over all the outputs of lots and lots of infinitely many neurons here, each one multiplied by a corresponding weight. And so we have a large sum over weights, which at least at initialization can be all random variables, let's say Gaussian random variables. And so when we have lots of those, we can use central limit theorem to figure out what's going on, at least statistically, with this neuron. So that's kind of at the heart of why it's a good idea to make these networks wider. And I'm not going to go into all those results, but I'm going to highlight one result that we're going to build on in this talk. And that's called the neural tangent kernel. This is a theorem that came out in 2018. And it roughly means the following. So you see well, before I say what the theorem is, I want to say that one of the challenges in understanding what's going on with these networks and why they perform as well as they do is that you sort of have to understand what's going on in the optimization process. You have to keep track of gradient descent and know what's going on there. And that's extremely hard because we have very little understanding of the dynamics of this gradient descent process. And so the neural tangent kernel was kind of a simplification that helped us understand the optimization process better. And what it says is that if you take a network and you make it infinitely wide and you normalize things properly so that the outputs don't blow up. So you take things very wide, you normalize things in a nice way, and you train it with gradient flow. So what that means is you take the learning rate to be infinitesimal. So actually, instead of taking discrete steps, you're doing a continuous path in the loss landscape. So it becomes a differential equation that optimizes the network. If you do all these things, then your optimization trajectory becomes equivalent to that of a linear model. So it becomes equivalent to just having a sort of dual landscape where you just have a linear dependence on the parameters, and you have a very simple optimization trajectory, which we understand how that works from convex optimization. Okay, and let me give kind of a sense of where this is coming from, and I hope that will kind of maybe help clarify this result a bit. So let's take our network function f. It's a function of the weights w and of the input x. Let's choose an initialization point at random, that's w naught, and we're going to do a Taylor expansion around this point. So we have the fixed term, which doesn't change as we're training the network, and then we have the linear term, which is linear in the displacement of the weights from their initial value as we're updating them, and then we have a quadratic term. It turns out that what's happening once you make the network very wide is that these weights don't move very far away from their initial value. You have so many weights to keep things from blowing up. Each one of them can't move too much from its initial value, and it ends up being that the linear approximation in this limit is enough to describe the whole network, even after you train it. Right? So once you make the network very wide, you can drop this quadratic term even after training, and this actually describes the full network. And you can see that this is nothing but a linear model, not exactly in the original parameters, but in the displacement of the parameters from their initial values. So you get just ordinary linear regression once you take this infinite width limit. And we understand how optimization for linear regression works. And so now we understand how the whole optimization trajectory works. We can actually solve for it analytically. And so this whole complicated deep network with nonlinearities on all this compositionality and so on becomes reduced to a linear model. The features of this linear model are given here. These are the gradients of the function at initialization. So you can think of these as taking the input and calculating a whole bunch, like infinitely many random features, or just random functions applied to this input, just set by whatever random value we set our initial values to. Okay, so this was a result.
So you had mentioned that this was a very sort of empirically efficient network. Shouldn't I be surprised that this simple linear model is so good then? Or if it reduces to this linear regression, why is it so performant?
Exactly. So that's a great question. I'm going to talk about that some more. This was a surprise. This was definitely a surprise. So I will talk about it some more. And of course, the answer is going to be that this theorem has some assumptions in it, and there's a loophole. Or there are actually many loopholes. So we're going to discuss one loophole in this talk, and we'll see how actually in practical settings the theorem gets violated. But that's going to be kind of the point of this talk. I just want to mention as a connection to physics that this theorem was proved using kind of I would say a standard computer science approach originally. We proposed another way to prove and understand this theorem, and also to extend it by using Feynman diagrams, more specifically a 't Hooft expansion. 't Hooft expansion here lets you actually do a 1/width expansion. So the n from the 't Hooft expansion corresponds to the width, and you can do a 1/width expansion. And you can actually say more than what this theorem does. You can calculate corrections. I won't have time to go into that, but I just want to mention briefly where the connection comes from. So the simplest connection comes if you take your network function f, you just remove all the nonlinearities, and you just have a big, what we call a deep linear model, where you have some weight vectors at the ends and weight matrices in the middle, and this is a model that's, it's just a linear function, but the gradient descent dynamics of this model are non-trivial, so it's an interesting thing to study theoretically. And if you look at this, and if you're familiar with the 't Hooft expansion, you'll see that this function is like a vertex in a vector model, like a vector matrix model that we have in particle physics. We have the vectors at the ends, and we have the matrices in the middle. And the sort of things that we like to calculate with it are expectation values of moments of this function, where the expectation value is over the different initializations of the weights. And these are typically taken to be Gaussian. And so the thing we can try to calculate are moments of vertices doing in a big Gaussian distribution, which is exactly the kind of thing that the Feynman diagrams, and more specifically the 't Hooft expansion, are good at. And so once you start taking gradient descent steps, you see that the things that you really want to calculate are all kinds of complicated moments like this. Here, the subscript corresponds to taking derivatives with respect to the weights with indices I and j, and these indices are tied. And so you can sort of take these complicated moments and translate them to double line diagrams and read off the scaling from the double line diagrams just using standard 't Hooft techniques. And you can figure out that some of these corrections are suppressed by 1/n, and with some more machinery, you can figure out that this everything boils down to a linear model like in the original theorem. And then you can go and calculate 1/n corrections. So I'm not going to go into the details there. I just want to point out that there's this connection between large width and a 't Hooft expansion. Okay, but now going back to this, the question that was asked is like, if it all boils down to linear models, how are they so good? And yeah, when the neural tangent kernel work came out, there was a lot of excitement. People thought, oh, did we actually, was deep learning actually solved? Like, is it all just linear models if we make it wide enough? And then people started experimenting and realized that it's not actually that simple. And I'm going to present this as this thing called the performance gap paradox, which is really two statements, two conflicting statements, just to make it kind of sharp. One is that, as I mentioned before, wider networks typically perform better. And just wider is just generally better. Here's a plot of this from 2017. You take a network, you train it on some image classification task, and you train a bunch of these, and you just keep increasing the width, the number of hidden networks. You just keep increasing and increasing, and you calculate the training error and the test error on the unseen data. And you see the training error quickly goes to 0. That means it manages to completely accurately recover the labels of the examples it has seen during training. So it memorized all the training data. And if you look at the training error, it does still keep going down even after everything was memorized. This is what I call the generalization paradox. Sorry. But this is an effect. So things get better with width. That's one observation. The other observation is the following. So if it's really just a linear model at infinite width, we can sort of jump to the infinite width network. We don't have to instantiate that directly because we can't put infinite width on a computer, but it is a linear model, so we can use this dual linear model description and just train that, because that linear model is controlled by a certain kernel that we can calculate, and so we can get at that infinite width model directly without actually having infinitely many neurons, and we can train that linear model and calculate its performance. And it turns out that doing that actually leads to worse performance than a typical network. Okay, so even though as we keep increasing the width, things get better and better and better, if we jump to infinite width, we get worse performance than a typical network. So it's not going to be whatever the error converges to here. The error is going to be higher. It's going to be somewhere here. That model is going to be worse. Right? So here are some numbers from a study that was done on a certain kind of neural network called, it's a convolutional network with some details in the architecture. Those don't really matter, but the point here is that here, instead of the error, they show the accuracy. So if you just train an ordinary network, you get accuracy on CFAR10, the data set we've seen in like 80-something% accuracy. And if you do the linear model version of that, so the so-called infinite width version of that, it's called CNTK, you see that it's significantly worse. Like here, like 7 percentage points is like much worse. And so this is a paradox. How can it be that things keep improving with width, but we jump to infinite width and things get worse? And so the answer is that it's going to be that there are loopholes to this theorem, and it's going to be interesting to see where the theorem actually holds. Where do we get an infinite width model that's a linear model, and where does this linear model thing not explain the actual behavior of the network, and can we come up with a new theory that will explain that? And that's going to be the work. That was all background, and I'll start describing the work that we did to kind of understand what's going on. So any questions so far?
Could it be that we just haven't gone to big enough sort of width that function's just not monotonic and it actually just ends up getting worse at some point?
Right. So that was like when I asked people why is this happening, that was the most common answer. Maybe it's just not wide enough. I mean, that could always be the case. The thing is that we can actually kind of know that's not the case using these Feynman diagram tools, because, well, we want to know if we are wide enough to already be in the asymptotic regime or not, right? And we can do that if we can calculate these 1/n corrections, which we can see if they capture what's going on well or not, right? So we know if we're like close to infinity or not. And the answer is yes. Already here, the 1/n corrections capture what's going on really well. And so we are already in this asymptotic regime. There's not much room for anything to blow up anymore. Yes. Okay, so to answer this, we kind of again have to go back to experiments and kind of try to map out what's going on. So this is an example of one of the early experiments we did in this project. So let me spend some time explaining what's going on here. So each point here is an experiment, or actually a pair of experiments, where we take a network, a fully connected network, and we train it on MNIST with a particular learning rate. That's the x-axis value here, and a particular batch size. Batch size means at each gradient descent step, how many examples are we actually showing the network? Usually we don't show all the examples at every step because that's very expensive. We sample a subset of the pictures and just put that, just calculate the loss on that. That's not going to be so important here. We're mainly going to care about how things change as we're training the learning rate. Okay, so we choose the learning rate, we choose the batch size, we train our network, which is a fairly wide network. And then we also train the corresponding linear model, and we compare them. How well do the predictions match? And the color represents how well these predictions match. So dark means there's very good prediction between the linear model and the actual network. So that means the predictions from the theorem hold. And a bright color means that there's a large discrepancy between the predictions of the linear model and the actual network. So the theory doesn't hold. So already we can see that there are these two regimes, or actually phases, it turns out, where there's good agreement with theory and bad agreement with theory, and there's this sort of thing here, critical line, that separates them. If we go all the way to the right, these yellow X's mean that none of the networks managed to train. So this is where learning rate is too high and we had a divergence in the optimization process. So that can also happen. And finally, like the most important point in this plot is this X mark, which is where we got the optimal performance on unseen data. And we see that the optimal performance is obtained deep in this region where the theory breaks down. So where the model does not behave like a linear model at all. Right? So we're going to try to understand what's going on here, why do these transitions happen, and kind of try to guess at why the best performance is happening here, even though that part is going to be a bit more speculative. But at least we'll have we can come up with a dynamical picture for why the theory breaks down and exactly when it breaks down. And of course, I mean, this is kind of maybe almost trivial for this audience, but when we saw this, we immediately kind of said, oh yeah, I mean, this looks like a phase diagram, right? And we would try to talk to folks from CS and say, oh yeah, it's like a phase diagram, and they would say like, what's a phase diagram? So this is something that's like deep in the consciousness of people coming from a physics background, but I learned is like not well known at all outside of physics. And so that was really helpful in doing this investigation, just having all that background and understanding phase transitions and how they work and so on, as you'll see. So I'm going to argue that they're actually like, the question? No. I'm going to argue that there are actually like three phases here with genuine phase transitions between them, including critical exponents that we can calculate. There's going to be a small learning rate phase where there's good agreement with theory. There's going to be a large learning rate phase where we get the best performance, but we have to develop new theory. And then there's going to be a divergent phase where the optimization doesn't actually work. And just to give a bit more sense of what's going on here when you're training networks, just to give more data of what's going on in the training process, there are a couple of interesting things that happen. So for example, you can look at the training loss as versus training time. So how does the training loss change as you're training the network? And each line here is training the network with a different learning rate. The lines here at the bottom are trained with like small learning rates, let's call them. And you can see that their training just progresses normally and the loss goes down and converges to a small value and everything is fine. And when we train them with a large learning rate, there's this dramatic effect that's happening where the loss initially shoots up really high, looks like it's diverging, but is actually just then converges just fine. Right? So this is a sort of seems to be a signature of this, what happens when you train with a large learning rate. Another thing that we can measure is the curvature. So the maximal eigenvalue of the Hessian. So here we're tuning the learning rate, we're training for a bit, and then we're measuring the curvature that we got to. And we see that for small learning rates, the curvature is more or less fixed. It's actually the same as its initial value. But once we cross a threshold in learning rate, we see that the curvature we end up with is going down dramatically. And this is interesting because I mentioned before that there's this negative correlation between curvature and performance. And so this is like one hint that maybe training with a large learning rate helps performance because maybe it's connected to the fact that the curvature is lower. But so far, these are just like some empirical observations about what's going on at small versus large learning rates. Okay, so the thing I like to do now is describe a toy model that we can solve pretty much, or at least in a physics sense, we can actually solve it, which captures all of these effects and kind of explains why the transitions happen, and also predicts where the transitions happen in terms of what learning rate can we expect to see these transitions, and explains these different empirical effects that we just saw. And it's going to be a very simple model. It's just going to be a network with 2 layers, so like one hidden layer. It's going to be a linear model. So as I mentioned before, we can just remove nonlinearities and still think about what's happening in gradient descent. So it's going to be just a linear model. It's going to be very wide. And we're going to analyze the gradient descent equations in this model as a function of the learning rate. And we're going to recover these phase transitions. And then if we have time, we'll go and connect the predictions that we get from this model to some modern networks, but I'm not sure we'll get there. So let's just look at the model. All right. So as I said, we're looking for a toy model that reproduces all of these effects. And again, it's going to be a very simple network. We have one-dimensional input. For the purpose of the talk, I'll just do this. I'm really going to use the simplest version. We can complicate it a little bit, but this already captures all the effects that we care about. So just one input, one real number as the input, one real number as the output. And then we have this wide layer of neurons in the middle. The width is going to be n. And we're actually not even going to train it on any sort of real data. We're just going to train it on a single training sample where the input is going to be 1. So we feed in 1 from here, and the label is going to be 0. So the output we expect that we're going to train on is just 0. So like this very, very, very simple setting where we're not actually learning anything. And so in this setting, this is going to be the function. There's an input here, x equals 1, which I just did not put in by hand, but it's here. And then we have the first weight matrix, which is actually a vector in this case, which is u. And we have the second weight matrix or vector, which is v, and then we get the output. So the function is just u transpose v. And we normalize it properly. This is the same normalization that's used in the neural tangent kernel work, so that when we take this number n to infinity, things don't blow up. So we normalize it like this by square root of n. And to complete the problem, we need to define a loss function. We're going to take the mean squared error loss, which in this case is just f squared because we set the label to 0. We can add more data points. We can have more. We can have non-zero labels, but the basic picture is going to be the same. And so this is our setup. U and v are going to be vectors in Rm. Okay. And so we're going to train this model. We're going to try to learn that whenever we put in 1, we need to get 0 out. And so we're going to do it with gradient descent. And these are the update equations for gradient descent. So the next step of u is going to be u minus learning rate eta times the gradient of the loss with respect to u, and similarly for v. And the challenge is now to, analyze these gradient descent equations and understand their dynamics as a function of the learning rate. There are 2 n equations here. And they're coupled. So even though the model is like as simple as it gets, this is still quite complicated. It's like we don't know how to solve these equations at all. So we have to introduce some tricks. So the main trick we're going to use is, instead of analyzing the equations in parameter space, u and v space, we're going to switch to thinking about them in function space. So instead of tracking each individual parameter, we're going to think about how the function as a whole evolves under gradient descent. And so this is the equation, the update equation for the function. So I update the weights with 1 step of gradient descent. This is what happens to the function. So we're going to have a new factor here, h, which I'm going to describe in a second. That's going to be the curvature. And then we're going to have another term, which is, I didn't write down explicitly. It's going to be 1/width suppressed term. So at large width, we can safely ignore it in this case. Now this h is the curvature. It's related to the Hessian. In this case, it's actually the trace of the Hessian. But what it is for this model is actually a very simple thing. It's just the sum of the norm squared of the 2 weight vectors. So this is all it is. So now to close this system of equations, we have to write down the update equation for h as well. And the nice thing is that because the model is so simple, the equations actually close on these 2 variables, and we don't have to keep introducing variables. So this is the update equation for the curvature, and it's just written in terms of the previous curvature. and the function. And so we've now reduced the problem for having two n equations to having just two equations. And this is really thanks to the simplicity of the model, the fact that we don't have any nonlinearities, the fact that we don't have additional layers. All these things are important to keep things as simple as possible. And so the next task is to analyze this pair of equations, the dynamics of these two equations as a function of the learning rate eta. That's our parameter. And so we take n to be very large, and we need to see what's going on as a function of eta. And that turns out to be manageable. So let's start analyzing these equations.
Can I ask?
So, yeah.
You seem to have dropped the 1 over n term in the f update rule, but you have kept it in the h update rule. Is that a consistent truncation?
Yes, yes. So we can actually do the whole analysis with this term. It turns, as you'll see, this 1 over n term is actually important. And please believe me that this 1 over n term is actually not important. Of course, to be sure, you have to include this and do you need to do the full analysis. But it turns out that you don't actually need to care about this term, but you do need to care about this term. Yeah. But it's definitely not consistent a priori to just drop this term and not this term. Yeah, thank you. Okay, so first let's look at the simplest version of this, which is what happens if we actually take infinite width. So we look at these equations and we really just chop off all the 1 over n terms. We chop off this term and just see what we're left with. And we get something very simple. We see that the curvature stays fixed at its initial value, and we see that the function evolves multiplicatively like this. If you write down the linear model and work out what the function evolves under gradient descent, or how the function evolves under gradient descent, you'll get exactly these equations. H is going to be the curvature, which is just, for a linear model, is just determined by the data itself. It doesn't care about where you are in parameter space, so it doesn't evolve during gradient descent. And the function gets these multiplicative updates. So if you think about it, for a linear model, you have this quadratic well that you're moving in. And if your learning rate is not too high, you get some measure of the curvature h, which is like the curvature of this quadratic well, and you're going to bounce around and converge to the minimum, like with these multiplicative updates. And so in this case, we get a linear model. So the model, so the nonlinear, the deep network we had reduces to a linear model. And the optimization will converge as long as the learning rate obeys this inequality, which is familiar from convex optimization. So this is just a well-known bound on the learning rate when we do this sort of quadratic optimization. So what we have here is we've recovered the neural tangent kernel theorem. We took the width to be infinite, and our model got reduced to a linear model, and we understand everything about the optimization trajectory. Okay, so great. But of course, we saw that there's something interesting that happens when the learning rate is too large, or larger than some value. And so we can guess that something changes once we cross this threshold, right? And so if we stay with the infinite width limit, as we increase the learning rate beyond a certain value, things will just diverge, right? But this is where the 1 over n terms that we dropped can become important, and actually do become important. So in this regime, the linear model diverges, but now we'll see that the full network with the finite width effects actually converges. And so we're going back now to the full equations with this extra 1 over n term, and we're going to see what's going on. And let's look specifically at what happens if we take the learning rate to be bigger than this critical value, but smaller than this other value. Let's see what's going on if we set that to be the learning rate. And so the first equation tells us that, yeah, f is going to start growing. So remember, the label is 0. So the minimum is going to be when f equals 0. We see that f is growing exponentially fast. But at the same time, something happens to the curvature h. It gets these additive corrections that are initially suppressed by 1 over n. But as f grows exponentially fast, they become important. We can't neglect them anymore. And as long as the learning rate is not too big, these corrections are going to be negative because of this factor here. So this is all positive. This factor here is going to stay negative. And so this is going to decrease the curvature. So while the function is blowing up, the curvature is dynamically getting decreased. once the curvature is low enough, this factor here that's controlling how f changes is going to be smaller than 1 in absolute value. And then once that happens, f is actually going to start shrinking again. It's going to shrink all the way to 0. And so we have convergence. So f is blowing up, curvature is going down. Once curvature is low enough, f is going to go down to 0 again, and optimization will succeed. And this whole thing happens very quickly because f grows exponentially fast. This whole process is going to be done in log of n steps, which for a typical neural network is going to be like an order 1 number of steps, basically. So if you measure every step what's going on, you'll see the loss blow up and then go down again. This is a caricature of these dynamics. We have two axes here. The weight correlation is like U transpose V, and we have the curvature, and the color here is how big the loss is. So the gradient descent is supposed to get to a point which is very dark. So you can see these are the points that gradient descent visits. With large learning rate, it starts at some value. You can see that the loss grows rapidly, but at the same time, curvature is going down. Once curvature is low enough, you can see that there's convergence to a minimum, and notice that this minimum has lower curvature than the neighborhood we started in. So we have this whole song and dance, and at the end we find a flatter minimum than we started with. So this is what we call the catapult dynamics. It's not a linear model anymore. There's something more complicated going on. And so this is sort of one loophole in this neural tangent kernel theorem. If you train with a learning rate that's too large, you don't get a linear model anymore. The full neural network dynamics are more rich. And so again, just to say, so in this catapult phase, when we train with a large learning rate, we get that the loss blows up and then goes down. So it looks like things are diverging, but actually everything is fine. It's just navigating to an area with lower curvature, and then it converges and it's all good. And then finally, if we increase the learning rate too high, then this factor here is going to become positive. The curvature is going to keep going up. The function is going to explode, and things are not going to, and optimization will just fail. So there's a maximum learning rate beyond which even the full neural network cannot train. All right, so I keep calling this a phase transition. It actually has all the hallmarks of a second order phase transition from physics. In particular, we can train the network very close to the critical learning rate, and we can measure the convergence time. And it turns out that right at the critical learning rate, this 2/h learning rate, the convergence time goes to infinity. And when we approach this critical value below or from above, the convergence time obeys a power law, and the critical exponent here is 1 theoretically, and we can go and measure it, and we get some fairly sensible values. And so you can have critical exponents, you have a divergence at this point, and so it kind of really feels like a second order phase transition. Okay, so let me summarize the predictions from this model. So everything we talked about has to do with mean squared error loss. I mentioned cross entropy loss before. There, the behavior is very different. So this is all about mean squared error loss. And so we found that there is a regime of learning rates where ordinary networks train, but they don't behave like linear models. For our toy model, So this regime starts with, once we cross this critical value 2 over the curvature. This turns out to be also borne out for modern networks, not just for the toy model. So basically every network we've tried where we've seen the phase transition, it happens at this value. For each network, we have to measure this curvature separately. We have to measure it empirically. But once we measure that, this is where the transition happens. The maximum learning rate where things break down, that is more network dependent. For the toy model, it was 4/h. For ordinary networks with ReLU, we empirically found that it's something like 12/h. So this is not, we don't fully understand this value, but 12/h seems to be a good predictor of the maximal learning rate. And so in this regime, we have the catapult effect where the loss grows to be very large. Specifically, it grows to be order of the width. and it does so within log of n steps. And the main point, I guess, is that the final curvature that you get to after this whole process happens is lower than the initial curvature, and we believe this has something to do with the better performance that we have in this phase. All right, so I just want to show, I want to skip ahead and just show, because I see I'm almost out of time. I just want to show a comparison of these predictions to just a modern neural network. So this is something called a wide ResNet. We're training it on CFAR10. This is a network that's like commonly used in practice, and we measure the test accuracy of this network as a function of the learning rate. The two dashed lines are predictions for where the large learning rate phase is happening. So 2 over lambda would be 2 over h, and 12 over h. And if what we say is correct, then the best performance should happen somewhere between these lines. Now there are some experimental issues with how to actually do a fair comparison of experiments and among different learning rates that I won't go into. But once we do a fair comparison, we see that, yeah, in this example, the best performance is actually obtained between these two different lines. So in that sense, we have a predictive theory, even though we started with a very simple toy model. Yeah, right. So let me summarize. What we've seen is that when we train networks with mean squared error, then gradient descent dynamics, once we make the network very wide, they fall into 3 separate learning rate phases. And specifically, the most interesting one for us is the large learning rate phase, where we have a deviation from existing theory. We can understand things with the toy model. We observe this huge bump in training loss, and we get the best performance. And we have some prediction for what window of learning rates we expect that to happen in, which we can apply to basically any network. So thank you. That's all I have. I think the lecture hall is muted.
Nope.
Oh, here we go.
There we go.
Thank you.
Right. Yeah, do we have any questions? Quick questions for the speaker?
I have a question. So in the plot that you showed of the batch size versus learning rate, at smaller batch size, the phase boundaries have this sort of slanted feature as opposed to being perfectly vertical. Do you have some sort of explanation for why that is the case? Could it be like finite size effects or something?
I don't have a full explanation for this, but it has something. Well, when you have lower batch size, basically what you have is more noise, because the gradient descent is meant to be in like a linear approximation of the. So you're doing a linear approximation. This is a finite step size effect. When you have a smaller batch size, what you're actually saying is we're not calculating the full gradient. We are calculating an approximation to the gradient by sampling some subset of terms that contribute to the loss. And so that introduces some stochastic noise into this process. We're not calculating the full gradient, just an approximation to the gradient. And I think, I'm not sure I can give very good into, well, let me just leave it at that. Like once you introduce this noise, that kind of shifts the phase transition earlier, because I guess just because of the noise, you're going to not do well with the linear model like earlier on. I don't think I have a very satisfying explanation for why that is, but it's basically because of the noise of the smaller batch sizes.
Thank you.
How does the depth of the network affect the qualitative picture that you have at the end, or does it not matter?
So for what I said now, it actually does not matter. Like this wide ResNet, for example, that I showed here. So I showed just the performance, but you can see like we can reproduce all of these effects on the wide ResNet. So You can see the loss blow up and then decay. You can see the curvature being constant for the small learning rates and then go down at the larger learning rates. And this is a fairly deep network. So the depth does not seem to matter at all for this, as long as it's wide enough. Yeah.
Is there anything interesting on zooming in, sort of on the critical regime? So, say like a double scaling limit, these tooth expansion matrix integrals. I guess you're just interested in performance, so it's not really maybe an interesting regime, but.
Yeah, right. That would be, we didn't dig too deep into the phase transition aspects of it, exactly because of what you said. This is kind of, I mean, if this was the physics system, then I think a lot of the focus would go there. But it's just that the stuff that people care about in machine learning is kind of different. Like if this is not the regime that gives you the best performance, then like it's like less interesting as a target. Yeah, that's kind of just the difference between the fields of where the research focuses, I would say. Yeah. Yeah, but it might be interesting to ask what happens close to the maximal learning rate. That I understand much less, or like what sets the maximal learning rate and what's the dynamics close to that. Because I mean, typically people try to push the learning rate as high as possible. I mean, I showed control experiments where the performance is better, but like if you remove the controls and you just train at a fixed compute budget, then like the larger learning rates do even better, kind of because they get there faster. You just take bigger steps and you get there faster. So there's just like an inherent advantage of bigger learning rates. So really just understanding what's the maximal learning rate that you can use beyond saying that it's in this window, that would be pretty nice. And there is another phase transition that happens there, a much more kind of straightforward one. Is just that things break down. So I think maybe understanding that could be an interesting question, even from a machine learning perspective. And I know very little about that.
Are there any other questions? Great. Well, let's thank our speaker one more time.
Well, this was a great talk. I think I actually followed it.